Hi, this is Mrs. LaBarbara. This is Physics Chapter 13, Modern Physics, Video 4. Today's topic is Models of an Atom, Part 2. The objectives are: know only certain energy levels are permitted in atoms. Understand an atom may be ionized if it absorbs a photon with great enough energy. Understand an electron can only jump to a higher energy level if it is hit with a photon with the matching energy to make that transition. Be able to determine the energy needed to liberate an electron from an atom, aka to ionize it. Be able to determine the photon energy needed or released to make an electron jump to a higher or a lower energy level. To be able to determine if it is possible for a particular photon to be emitted by a specific energy transition, and to be able to determine the number of possible photon energies emitted during a specific set of transitions to a lower energy state.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 135. It's on the wave model of an electron. Remember, as we look at the level of an electron, we see that they don't behave like particles, but act more like waves. And it was this wave model that allowed us to really understand what was going on at this classical level of a Bohr atom. And so we realized that electrons could be here, or here, or here, but they didn't exist in the middle, and that was puzzling to scientists. Also, why is it when an electron falls down, it emits a photon of light, this certain amount of energy? Well, the wave model unlocked that because we've really got a good understanding of how waves work. So if we have waves moving back and forth, they create something called a standing wave. And so what scientists started to hypothesize is maybe the electrons, as they're moving around, are interfering with themselves. They're going so fast that they're interfering with the electrons as they come around again. And so maybe they're wrapping around and creating standing waves. And so areas out here, we could get a standing wave where the electron moving around the outside of the atom is interfering with the electron itself. And so what you get are these standing waves that build up, and that's where that energy allows the electron to be there. But in between these different orbits, they don't match up perfectly. And so they have to be a whole integer of the wavelength, the de Broglie wavelength, for the electron to exist. If it doesn't match up perfectly, then the electron annihilates itself. And so electrons can only exist in certain energy states. And so the wave model allows us to understand this at the level of standing waves. And so standing waves occur when the waves are interfering with themselves. And so the de Broglie wavelength showed us what that wavelength is, and then we could use that to calculate the momentum and even figure out what's the size of the atom itself. Another important thing it showed us is that as electrons fall to a lower energy level, that energy contained within that standing wave is released in the form of a photon that we can see in these spectral lines. So to really understand what's going on with these wave electrons is we could think about fundamentals and harmonics. And so when you strum a guitar, this would be the first fundamental. This would be the second fundamental, the third fundamental. So using that as a model, if we're looking at electrons, they're moving out from the center with different wavelengths as well. And so let's start with the first inner electron. What's really going on is one wavelength is wrapping around the atom itself. What would that look like if we look here at this first orbital? It's going to look like that. Now we know something about the momentum of the electron. We can calculate the de Broglie wavelength, and if we plug it into this equation, this here is just the circumference of that circle, we can figure out what's the size of the atom, and it ends up matching up with the Bohr radius that we'd measured before, 0.53 angstroms. Now what is the next level going to look like? Well, we have to have two wavelengths in there. So what's that going to look like? It looks like that. And if we go to 3 wavelengths, we're going to have a different de Broglie wavelength. And so what are we going to get? It's going to wrap around like that. And so what's happening is the electrons are racing around, interfering with themselves. They're building up energy in that one energy level. Now what's interesting about that is as they fall back down, they release that energy in the form of a photon. How do they jump back up to a higher level? They have to absorb that photon. And that starts to explain why we see these spectral lines. And so did you learn to qualitatively link together the wave model for electrons and then the different energy energy states in an atom? I hope so, and I hope that was helpful.
Okay, so that is de Broglie actually proved Bohr models is valid. Okay, now let's do a couple of examples. Which photon energy could be absorbed by a hydrogen atom that is in n equals to 3 state? So here is n equals to 3 state. So n can it can absorb the energy, say, in order to go to 4, how much energy does need to be absorbed? That will be 0.66. So how did I get 0.66? I use negative 0.85 minus negative 1.51. I have 0.66. So in order to go 3 to 4. So all the others doesn't match anything. So this is the only one that matches. Another example, a photon strikes the electron in the ground state of the hydrogen atom, liberating the electron. What is the minimum energy in EV did this photon have? So in order to liberate electron in the ground state, electron must absorb the least is 13.6 electron volts. How much of this energy is in joules? To convert the electron volts to joules, remember we multiply by this number, 16 times 10 to the negative 19 joules. We have 2.176 times 10 to the negative 18 joules. What is the frequency of the photon that could provide this energy? Remember E equals to H times F. So E is 2.176 times 10 to the negative 18, and H is Planck's constant, 6.63 times 10 to the negative 34 joules a time second. That's how you have 1 over second. 1 over second is hertz, which is 3.28 times 10 to the 15 hertz. Another example, what happens to an electron in the n equals to 2 state of hydrogen if it is hit by a 5.4 electron volt photon? So let's see, n equals to 2, you have negative 3.4 electron volts. So your energy after would be positive 2.0 electron volts. So what's going to happen to that electron in n equals to 2 state? It is going to be ionized, and you'll have extra 2.0 electron volts. That is kinetic energy. So the electron will leave the atom with a kinetic energy of 2.0 electron volts. Another example, an electron in a hydrogen atom drops from n equals to 3 energy level to n equals to 2 level. N equals to 3 is negative 1.51, n equals to 2 is negative 3.40. What is the energy emitted? Energy emitted is the difference between the two levels. So you use negative 1.51 minus negative 3.40, you should have positive 1.89 electron volts. What is the energy in joules? To convert electron volts to joules, you'll multiply by 1.6 times 10 to the negative 19. So you get a number. Then what is the frequency? To find the frequency, you have to use E equals to H times F. The E has to be in joules in that equation. So you find its frequency. Next one says what color is the emitted photon. You'll have to check your reference table. So first you do the energy difference to find the energy in electron volts. Then you convert the electron volts to joules. Then you use E equals to H times F to find frequency, which is 4.56 times 10 to the 14 hertz. This is, check your reference table, this corresponding to the red light. The color is red. Another example, when electrons drop from one energy level to another, they can follow any path to the lower state, which each downward step produces a photon with different energy. For example, how many different photons could be produced in a transition from n equals to 4 level of hydrogen to n equals to 1 level? So n equals to 4 to n equals to 1. So there are many ways to go down. 4 can directly go to 1, or 4 can go to 2, then 2 can go to 1. or 4 can go to 3. Now from 3 can go directly to 1, or 3 can go to 2, then 2 go to 1 again. So how many possible photons could be produced? 1, 2, 3, 4, 5, 6. Oh, 6 possible photons. Let's try again. How many different photons could be produced in a transition from D level to B level? D, C, B, from D to B. Try it yourself. See if you can figure it out. So the answer actually is 3 possible photons. Another example. What is the minimum energy required to excite a mercury atom initially in the ground state? So the minimum is go from A to B. So what is the energy required from A to B? Just do the difference in energy, which is 4.64 electron volts. Another example. A photon with a wavelength of 2.29 times 10 to negative 7 meters strikes a mercury atom in the ground state. The photon can be absorbed by the mercury atom because it will accommodate an energy level to what? If you go from the ground state, you absorb the energy. Obviously, you will not be able to stay in the ground state. So it has to be either B, D, or E. So let's see. The first we have to see how much energy is in joules here. Then we convert that joules back to electron volts. Remember, joules to electron volts, we have to divide by 1.6 times 10 to the negative 19. So we have 5.43 electron volts. Now, originally, you'll have negative 10.38 electron volts. When you add to 5.43, you will have a negative 4.95. This one should be point. So 4.95 corresponding to level D. So that should be level D, not B here. Okay. Level D, by the way, here. Okay, another example. As a mercury atom absorbs a photon of energy, an electron in the atom changes from energy level D to energy level E. Calculate frequency absorbed of this photon. So from D to E, take a look at energy level 1.24 electron volts. Again, convert electron volts to joules. You multiply by 1.6 times 10 to the negative 19. So this is how many joules. To find frequency, you have to use frequency equals to E divided by Planck's constant. So you will have 2.99 times 10 to the 14 hertz. Another example, electron in the C level of the mercury atom returns to ground state, which photon energy could not be emitted by the atom during this process. So this is from C level to ground state. So C can go to B, and B can go to A, or C can go to A. So there's 3 possible ways to go from C to A. So if C go to B first, you will emit 0.22 electron volts. The first one is possible. If then B go to A, you will emit 4.64 electron volts. So second one is possible. C can go to A directly, which will emit 4.86 electron volts. So the third one is possible. The last one is the one that's not possible. Okay, so that was Bohr's model. So from the video in the last lesson, you also heard a cloud model or Schrodinger model. So in this model, we know electrons are not confined to specific orbits because electrons essentially are waves. So instead, they are spread out in space in a form called electron cloud. So electron cloud is densest in the region where the probability of finding the electron is highest. That's where you'll have the highest amplitude for the wave, right? The cloud model represents a sort of history of where the electron has probably been and where it is likely to be going to. As you can see in this dark region, that's where most likely you will find electrons right around there. That's it for today. Thanks for watching.